to... I think it's working. I'm just not close enough. I'll hand over to Norbert to introduce.
Yes, thank you. Yeah, it's a great pleasure to have Professor Ian Roederer of the North Carolina State University with us today. He did his PhD in 2010 at the University of Texas in Austin. And then he went to Pasadena in California to be a Carnegie Fellow for 3 years. And then he was at the University of Michigan at Ann Arbor before he moved to North Carolina State University in 2023, where he's now an associate professor, tenured recently. So congratulations to that. Yeah, and Ian has done a lot of great work on ultraviolet spectroscopy from space, in particular using the HST and STIS with detections of many elements that some of you might perhaps not even have heard of, like holmium and whatever, with the aim of investigating the chemical enrichment history of the galaxy and studying nucleosynthesis processes. And he's also interested in metal poor stars. So yeah, we will hear about upcoming opportunities for metal poor stars as well, I guess, today. So yes, we are looking forward to your talk. And Rosalie also is looking forward to it.
Thank you. Yeah, it's always a pleasure to be here. Thank you, Norbert, and to the committee for the invitation to join you. Yeah, understanding the origin of the elements is one of the major challenges of modern astrophysics. And today I will share with you some of the ways that UV spectroscopy has advanced our understanding of stellar nucleosynthesis in particular. So you can think of this as the story of how elements all across the periodic table have been made. Specifically, how the elements produced in the Big Bang have been cycled and recycled through stars to produce the rich diversity of elements that we find today in the solar system and throughout the cosmos. Let's put that chemical history in a bigger context. So the figure here shows a schematic of the history of the universe. The Big Bang is on the left, and we today are on the right-hand side. The first stars formed just a few 100 million years after the Big Bang. Those stars formed from just the primordial hydrogen, helium, and lithium created in the Big Bang. Lived no more than a few million years. They were massive, probably lived no more than a few million years, and returned some of the metals that they produced back into the star-forming gas. So carbon, oxygen, calcium, iron, zinc, all of these elements and everything in between was already present in the star-forming gas more than 13 billion years ago. So as more stars form, those stars produce more metals, they return some of them to the star-forming gas, more stars form, produce more metals, return some of those to the star-forming gas, and so on. And you know, at some level, I think just about everyone in the room is probably working on these metals in some way, either identifying where they are or studying what they can tell us about the history of the universe and the objects that we find here. One of the big questions in my field is, what is the collective set of processes by which stars convert those light elements into everything else? And collectively, those processes are known as stellar nucleosynthesis. So in terms of how we do this, here's a brief schematic that you can use to help build some intuition. So the abundances of elements that you observe in the universe are some product of the nuclear properties and the physical conditions. If you know any two of these, you can deduce the third. So if the nuclear data are known, you derive the abundances in a suitable star, or a pre-solar grain, or a cloud of gas in the ISM, or the IGM, or the CGM, and In principle, you can infer the conditions at the time of nucleosynthesis. One kind of nucleosynthesis that I find interesting is what we call the R process, the rapid neutron capture process. The R process is one of the fundamental ways that stars and stellar remnants produce the heaviest elements. And it uses a rapid burst of neutrons to overwhelm and grow the mass of lighter nuclei. You can imagine this might require an explosive environment with high neutron densities. So we can watch an animation of the R process here as it runs along the chart of the nuclides. This is number of protons plotted against number of neutrons. All the black dots mark individual stable isotopes. The flow of the R process here is going to be marked by the bright colors. So I'll start the simulation, and you can notice that the R process shoots up from the light elements to the heavy ones. That happens in only a fraction of a second. And once that flow of neutrons shuts off, all of those heavy, neutron-rich, radioactive nuclei will decay back to the stable ones. The R process is the dominant source of the heavy elements that we find in the oldest stars, and ancient R process events in other stars produced about half of the heavy elements that we find today in the sun and on the Earth. Collisions of neutron stars are one confirmed site of the R process. So this animation is modeled on the famous GW 1708-17 event that occurred, well, was detected 9 years ago. It was the first event. It was detected in both gravitational waves and electromagnetic radiation. And you can see from this animation all of those different components of the ejecta. The few that I would like to focus on are the ones, sort of the brightly colored pieces of ejecta down near the center. This is called a kilonova, and this is powered by the radioactive decay of probably of order a few hundredths of a solar mass of freshly produced heavy elements, mostly lanthanides probably. So this is a kilonova. This is one confirmed site of the R process. Once you know something about that site or the R process, then that actually opens up all kinds of new questions that we've had for a long time, but now become within reach potentially. How exactly were the elements from iron to uranium made? Observations seem to indicate that at least one additional site of R process nucleosynthesis has been active. What is that site? Are there other sites? What are the detailed physical conditions of each of those sites? Which elements do they produce, and in what amounts? Once you know something about the physics of the R process and the sites where it occurs, you can then use that information to learn something else about the history of the universe or the objects that are here. And in fact, these questions, not just the R process, but the origin of the elements more generally, connect to nearly half of the scientific themes that were identified by the most recent Astronet science roadmap for European astronomy. This is first stars, first galaxies, first black holes, galaxy formation and evolution, stellar evolution, the deaths of stars, and the origin of astronomical transients, and then of course the conditions that are necessary for life to emerge. And at some point in the talk today, I will try to reference each of these different topics, maybe briefly, but at least as they connect to the story of the origin of the elements. So here's a brief introduction to my team at NC State University. Shivani Shah is a postdoc working to connect stellar abundances to kilonova observations, among other things. Pranav Charvu is a graduate student in my group, working on the signatures of low metallicity stars that you might find in ultraviolet. Jinghai Liu is a graduate student working with Gail McLaughlin and myself on theoretical aspects related to the R process. And then Zarina, Kate, Thomas, and Cameron are undergraduate bachelor students in my group Three of them are shown here at a photo recently taken at a meeting of the American Astronomical Society where they got to present posters on their work. Super proud of them. Well done. So this is my team at NC State. And I'm also a co-founder and a member of a group called the R-Process Alliance. We are a collection of folks from the astrophysics and nuclear physics communities with an interest in solving big questions related to the R process. And a fair amount of the work that I will show you today was produced as part of this R Process Alliance. Okay, with that background, here's an outline for what we'll do today. I will start off with an introduction to how the UV is beneficial to this kind of science. We'll look at an example of how the combination of UV and optical spectra together can reveal that the R process produces nuclei with masses greater than 260, potentially. We'll look at 5 different examples of elements other than R process elements where the UV has advanced our understanding of stellar nucleosynthesis in some way. And then I will conclude by proposing a UV path to the first stars. So let's start with topic 1 here. How does UV help us? And I'm going to do a little bit of a winding introduction to get there. I hope makes sense in retrospect. You cannot reproduce the R process in a laboratory. It's just too extreme. The photo here shows an aerial view of a region called Yucca Flats in the Nevada test site in the western United States. All of those sort of shaded regions are craters excavated by subterranean nuclear explosions on land that was stolen from the indigenous Western Shoshone tribal nation. Over the course of several decades in the last century, more than 1,000 nuclear devices were detonated here. 23 of those tests were conducted with the purpose of producing and studying the heaviest radioactive isotopes possible. Now, those tests were not true analogs of the R process because the astrophysical R process, the cosmic one, occurs over longer timescales and at higher temperatures. So you get some information from these tests, but it is limited, and the testing program was ended in 1992. Now, of course, we do have an example of an R process event caught in the act. This is the well-known 2017 merger that I mentioned a few minutes ago. This occurred, of course, in the outskirts of a galaxy located 40 megaparsecs away. And then you make the association between the R process and that kilonova by comparing the colors and the decay timescales with the expected opacities of radiation passing through millions and millions of transitions of freshly produced heavy elements, again, thought to be dominated mostly by lanthanides. Even so, you don't have a detailed element by element picture of what elements are produced in that kilonova. And this figure explains why. So the figure here shows predicted flux distributions spectra for an event like that 2017 event. And from top to bottom, you can see the effect of going from relatively low velocities to relatively high velocities. So the ejecta in that 2017 event were moving at between 10 and 30% of the speed of light. And at those speeds, any lines that are present that give you some detection signal of individual elements, those lines just completely blur together. Now, we have some information there, and there have been several tentative detections of elements in the kilonova aftermath of that 2017 event. The figure on the left shows the time series evolution of spectra of that event with some potential detections of strontium. That's shown by the red shaded regions. At the bottom, some potential detections of yttrium, and on the right, some potential detections of tellurium. This is hard work, and there are several groups around the world working to model these opacities. But it's hard, but I think this is an extremely interesting way forward if you can connect these signatures back to the elements themselves. So I'm really looking forward to seeing how this goes over the next 5 or 10 years and what new information might be learned. But even so, all that platinum and gold that you kept hearing about in the press releases, in the news coverage, it's all inferred, not observed directly. And that finally brings us to the UV. UV spectra of stars like this are the only places you can actually detect elements like platinum and gold. To the best of my knowledge, there have been a total of 8 detections of gold in other stars that are useful for studying nucleosynthesis. The figures here show 7 of them. The 8th one just didn't publish a figure. But you can do this for platinum and gold and all kinds of other heavy elements of interest. What is it about the UV? It's not magical. There's nothing magical about the UV that enables these detections. There are 3 big things, as I see it, that are beneficial here. First is that there are many more lines in the UV part of the spectrum. So that helps you by improving your statistical uncertainties, and it gives you opportunities to cross-check potential identifications if the identity of the absorber is in any way in question. Next, it gives you a wider range of electronic transition properties. And that's helpful if you're trying to build a better model. So if, for example, you're trying to build a better model of radiative transfer or a better model of a stellar atmosphere, UV transitions give you new or at least different constraints on your modeling. And the third thing is that the UV gives you access to more elements and more species than you could otherwise detect from optical or near IR spectra alone. Here are some examples of additional elements and species that you generally cannot detect in optical or near IR spectra of stars. These are all little zoom-ins around particular spectral features in the UV spectrum of a bright metal-poor star that happens to be enhanced in our process elements. This is HD 222925. Many of these elements have only been detected in a handful of stars that are useful for studying nucleosynthesis. Typically less than 10, sometimes just 1 or 2. So that's a challenge, but the advance here is having access to that UV. And if you put all that together, this is the rich periodic table that you get. This particular star, HD 222925, has the best known chemical inventory of any object beyond the solar system. 65 elements have been detected in this star. And the periodic table here is shaded, colored in, by which wavelength range each of those elements were detected in. So for most of this talk, I will define UV as short of the atmospheric cutoff. So elements that you must go above Earth's atmosphere to actually detect radiation at that wavelength. So roughly 3,000 angstroms. Somewhere between 3,000 and 3,050 is where that drop happens. So that's the UV that I'm talking about here that's shaded in blue. And the upshot of all of this is that the UV spectrum gives you a 50% increase in the number of elements you can potentially detect in other stars. For this talk, again, for context, that means sort of FGK type stars. Here's one example of a star where having access to the UV has improved the chemical inventory. The figure shows the heavy element abundance pattern in this star. So that's log of the abundance as a function of atomic number. The black dots mark the abundances of elements detected in this star, and the blue shaded regions mark elements for which UV was required for their detection. And you can see that the UV really starts to fill in some of those gaps between the elements that you would otherwise only have if you only had access to telescopes on the ground. In this case, what do we learn from this? We're not just trying to collect stamps, collect elements. We want to learn something too. And in this case, when you start to fill in that pattern, that gives you additional constraints on whatever model it is you're trying to fit to the nucleosynthetic origin of those elements. In this case, this is an S-process enhanced star, the slow neutron capture process. So this star is in a binary system with another star that was initially more massive. That star evolved, passed through the AGB phase of evolution, produced S-process elements, deposited some of those S-process elements on the star that we see today, and then turned into a white dwarf. So the star that we see today did not create these elements, but having this pattern gives you a lot of constraints on nature, the characteristics of that other companion star. So that's one way you can play this game. Here's another example of a star where having access to the UV improved the chemical inventory. This is the star we saw a few minutes ago, HD 222925. Again, log of the abundance versus atomic number. Blue shaded regions are the elements for which you needed UV. And we can detect 42 R-process elements in this star. And the nucleosynthetic interpretation here is that the claim, I guess I should say the claim, is that the heavy element abundances in this star reflect the yields of a single R-process event, or at least are dominated by a single R-process event that occurred early in the history of the universe, and then enriched the gas from which this star formed. So with that claim, what do you learn? Well, if you have a favorite model for R-process nucleosynthesis in a kilonova or some kind of rare supernova that might host the R-process, this is a template that you can compare your model predictions against. This is also not the only R-process enhanced star that we know about. R-process enhanced stars are stars that have, I guess put simply, large amounts of R-process elements, heavy elements produced by the R-process relative to their overall metallicity. These kinds of stars have been known for more than 3 decades now. This is not the first one known, it's not the only one known, and depending exactly on how you count, there are several hundred of these stars known today, and some folks in the room have been central to this effort over that time. But can we use this abundance pattern, this star, to help interpret that large amount of data that already exists for other R-process enhanced stars? Let's try that. And let's do it in the context of the heaviest nuclei that you could produce in nature. The R-process almost certainly produces elements heavier than uranium. We call these elements transuranic elements. They're the ones that are shown with the orange boxes here. Transuranic nuclei are inherently radioactive, highly radioactive, and they quickly decay into other things, and that's why transuranic elements have not been detected in the cosmos or in any real measurable quantity here on Earth. Fission is one of the major decay channels for transuranic nuclei. In that fission process, we'll produce 2 lighter neutron-rich nuclei. It produces energy in the form of gamma rays and a handful of free neutrons. Those 2 lighter nuclei will decay back to stability, and at the end of that process, they will populate elements listed near the middle of the periodic table. The probabilistic nature of fission leads to dozens of combinations of lighter mass nuclei from a population of a single parent isotope. So the distribution in mass of the fission fragments is bimodal, typically. There's a lighter peak and a heavier peak. So let's use abundance signatures in stars to potentially learn something about those transuranic nuclei. So we performed a meta-analysis of the abundance patterns of 42 R-process enhanced stars. It's all literature data. There's nothing new here. It's based on the combined optical and UV data, whenever that UV data are present. and we're sort of guided in our interpretation here by that star we looked at a moment ago, HD 222925. So the figure here is a sketch of how we'll illustrate the results. So the vertical axis shows the log of the abundance ratio for various pairs of elements. The horizontal axis shows europium to iron ratio, which you can think of as a proxy for the overall strength of the R process event that enriched each of these stars. And each point in this figure will be one ratio in one of these 42 stars. If there's a flat trend in that diagram, that tells us that those two elements are being co-produced in the R process. If there's a non-zero positive slope, that tells us that one element is being produced more than the other one as the R process gets stronger. So here are the results. They are separated into 5 different panels, ordered by increasing atomic number. So the pairs of elements in panels A, C, and D exhibit no significant positive slopes, telling us that they are co-produced in the R process. The pairs of elements in panel B and in panel E exhibit a significant positive slope, so they are correlated with each other and with the overall strength of the R process. One characteristic of a stronger R process might be greater production of transuranic nuclei, and therefore greater production of their fission fragments. So we can tentatively associate the elements in panel B with that lighter fission fragment peak. This is ruthenium, rhodium, palladium, and silver, elements 44 through 47. And we can associate the elements in panel E with that heavier fission fragment peak and elements that just naturally require a stronger R process, maybe for a slight enhancement in their production in the first place. I'm not aware of any other nucleosynthesis process that could do this, and this is the best explanation we have at present for these signatures. So what can we learn from this potentially? Well, these signatures are found in a fair fraction of metal poor stars, indicating that if this interpretation is correct, that these signatures may have been relatively commonly produced by our process events in the early universe. If they're common in the early universe, then perhaps that might naturally support searching for these kinds of signatures in the kilonova aftermath of neutron star mergers that occur today. And so I think this is potentially good support for having these targeted opportunity observing programs for any kilonova that might exist. If you want to trigger with JWST or something else, to look for the decay signatures of transuranic elements in that kilonova aftermath, not necessarily right after the event, right? This is relatively long time scales, months after the event. For example, from Californium-254, which is a transuranic nucleus with a relatively long half-life. And finally, you can infer the masses of the fissioning transuranic nuclei by simply adding up the mass numbers of their fragments. And if you do that, you find that masses greater than 260 are required. Now that mass is not yet in the range of the super heavies, or in the range where the nuclear physicists propose the existence of an island of relative stability. That's somewhere in the neighborhood of masses between 290 and 300. But it's moving in that direction. And it's already heavier than the mass of the heaviest isotope that has been identified in the debris from the nuclear weapons tests. So maybe it's not surprising, but the cosmic R process events might be more extreme than our terrestrial tests. Okay, let's move on to 5 brief examples of elements other than our process elements where UV has done something to advance our understanding of the nucleosynthesis. Let's start with arsenic. This is element 33. Arsenic only has transitions in the UV spectrum of stars. The figure here shows the heavy element abundance pattern. Again, log of the abundance versus atomic number. This is one bright metal poor star. Because that star is bright, you can get very high quality optical and UV spectra for that star. High quality spectra enable you to detect many elements. Many elements allow you to detect or place very strong constraints on the nucleosynthetic origin of those elements. And in the case of this star, there was no combination of an R process or S process material that could reproduce the observed pattern. And this is especially true for elements over on the left-hand side of the diagram, like arsenic and its immediate neighbors, germanium and selenium. It's only when a third neutron capture component was included, the so-called I process, that you could even begin to get something that looks like a reasonable fit for the abundance pattern in this star. Now that I process has neutron densities that are intermediate. The I is for intermediate, between that of the R process and the S process. That I process has evidence, observational evidence for its existence in relatively metal-rich environments, basically any place where you have protons being convectively mixed into the helium-burning layer of a star. And this star indicates that that I process might also be occurring in relatively low metallicity environments. Germanium. There are several absorption lines of germanium you can sometimes detect in sort of the last few hundred angstroms of ground-based blue UV spectra. Those lines are tricky and quite blended. There are several germanium lines in metal poor stars that are good abundance indicators in the UV. So the figure here shows the germanium to iron ratio as a function of europium to iron. And again, you can think of that europium to iron ratio as a proxy for the overall strength of the R process event that enriched each of these stars. Each dot here is a different star. And what you immediately notice is that germanium is completely uncorrelated with europium. So the interpretation of this was that germanium is not being produced in any measurable quantity by the R process. What is the origin of germanium then? I don't know. That's still an open question. Probably one or more nucleosynthesis processes that are associated with core collapse supernovae in some ways, but that's still an open question, and we're still collecting data on this to get a better idea. Zinc. Now, maybe it's surprising to see zinc here because there are a number of good zinc abundance indicators in optical spectra that get used all the time, and that's what the red dots are on the right-hand side of this diagram. But as you go to lower zinc abundances, lower metallicities on average, those optical lines eventually get too weak to detect. And there are intrinsically stronger zinc lines in the UV. Zinc has even been detected in one of the most iron-poor stars known, HE 1327-2326. This star is thought to have inherited its metals from a single population 3 supernova that occurred early in the history of the universe. The zinc to iron ratio in this star is enhanced, and that ratio, along with other ratios among other metals in the star, seem to favor metal production in an aspherical hypernova, perhaps. Phosphorus. This is one of the building blocks of life, right? Phosphorus plays an important structural role in DNA and RNA on Earth. It also plays an important role in energy generation in cells on Earth. So if you're thinking about life in the universe, it might be, worthwhile considering the availability of phosphorus as one potential route to life in the universe. Phosphorus has some lines that you can detect in the near IR part of the spectrum. But again, as for zinc, as you go to lower metallicities, lower phosphorus abundances, those lines that you can detect from the ground get too weak to detect eventually. And you can only detect phosphorus in low metallicity stars from the intrinsically stronger lines of phosphorus in the UV. When you do that, and you compare with, chemical evolution models for the galaxy, relatively simple models, but still, this is what you have limited data. Simple models probably okay. You find that you need a phosphorus contribution from at least some kind of hypernovae, and that the phosphorus yields from sort of run-of-the-mill core collapse supernovae need to be increased by about a factor of 3 to reproduce the stellar data. Boron. It's a light element, and it has a long history of study, both with the Hubble Space Telescope in the first decade with Hubble, and going back before Hubble, in fact. Today, Hubble is the only source of high-resolution UV data, but a long time ago, there was the IUE, and boron was being studied with the IUE even then. The figure here shows log with a boron abundance versus metallicity, and there have actually been, boron has been studied in more than just the 6 stars that are shown here. This is just the latest figure that I found from last year, and I think this was like their highest quality sample or something like that. But what we learned from this is that boron behaves like a primary element, which is to say that its abundance in stars does not seem to depend on the existence of some other metal in the star. And that's strange because one of the main boron production mechanisms is thought to be cosmic ray spallation on CNO nuclei in the ISM. And if that were the case, you'd expect boron to behave like a secondary element, that lower line shown in the figure. And so the way to reconcile this seems to be that you have some sort of high energy neutrino spallation process that occurs on carbon-12 nuclei in supernovae, where the carbon-12 was itself produced in the stellar interior shortly before the supernova explosion. So in that way, you always have the carbon-12. If you always have the neutrinos, you always get the boron as well, and it looks like a primary element. And so these data seem to indicate that boron was being produced by this neutrino spallation process even in the early universe. All right, so that brings us back to the beginning, or at least the top of the periodic table. And let me conclude here by proposing a UV path to the first stars. First stars ended the cosmic dark ages. Those first stars formed, as we've said, from the primordial hydrogen, helium, and lithium left over after the Big Bang. This animation shows the ionizing radiation emitted by those first stars as their protogalaxy forms. It's a little bit hard to see. Maybe that's a metaphor. I don't know. So the first stars produced the first metals. Those metals enriched the ISM, maybe left behind the first black holes as well. So understanding these first stars is important, but no metal-free stars have yet been found. So that begs the question, well, what were the first stars like? And a lot of people, including many of you in this room, are aiming to address this question. Virtually every large stellar survey that is ongoing or planned for the next decade has the first stars as one of their highlighted science cases. And most major telescope facilities do as well. And what I like about this, what I think is so exciting, is the wide diversity of approaches that all of these different surveys and telescopes plan to use to address this question of what were the first stars like. So this is everything from the shape of the 21 centimeter power spectrum to looking for highly lensed, highly magnified, high redshift objects, which AWST. And this is everything from absorption lines in high redshift damp Lyman alpha systems to absorption lines in low metallicity stars in our own Milky Way. So while I'm here to promote the virtues of UV spectroscopy, let's briefly talk about how 2 of these projects could potentially transform our understanding of the first stars. So first, the ELT. The ANDES instrument is the high resolution shell for the ELT. And it doesn't really go deep into the UV, but if you count UV as somewhere short of 4,000 angstroms or the Balmer jump, depending on how you want to define that, the ANDES does have a U-band, I think has been approved for the final design. And And that's super exciting. I don't have a whole lot I need to say here other than this is a 39-meter aperture. And of course, that pushes you out much further into the halo or into the local group where you could potentially study low metallicity objects, including candidate metal-free or second-generation stars. And so that's just going to be a big advance right there. So I don't have a whole lot to say here other than I think this is really cool. I'm glad this is being built. I'm glad there's a U-band included. The other telescope I'd like to talk about is the Habitable Worlds Observatory. This is NASA's next big flagship mission with a high-resolution UV spectrograph, probably almost certainly included on board. Now, the name of Habitable Worlds here gives away the top-line science case. But this telescope, this mission, would be transformational for virtually all areas of astrophysics, including the first stars. So let's look at a couple ways that habitable worlds could do this. And the main advance we're looking for here is increased sensitivity relative to the Hubble Space Telescope. Even just a quick glance at a model spectrum of a second-generation star shows that the UV has many more lines potentially available for analysis than the optical does by itself. Periodic tables at the bottom here show the numbers of elements and which element you could potentially detect in these different spectral ranges. In the optical, you get about 10 elements, give or take. And if you have a UV spectrum here, I'm defining this as short of the Balmer jump, you can detect up to maybe 19 elements, something like that. There's a bit of overlap between those two groups, but if you put them together, you get 23 elements potentially detectable in a second-generation star. What is that? That is the set of metals produced by potentially one population 3 supernova. The more elements you have, the better the constraints you get on that first star. The other way you can do this is by pushing the detection thresholds to levels that are much lower than what you could do just from optical spectra alone. So the figures here show 4 different regions of the UV spectrum. It's mostly synthetic spectra. There's one observed spectrum there overlaid for comparison around lines of magnesium, iron, carbon, and silicon. The reason you can push detection thresholds in the UV is because you're dealing with intrinsically stronger lines at the conditions that are typically found in late type stellar atmospheres. And these lines arise from electrons in typically the dominant population reservoirs under those conditions. So if we think about magnesium at the top there as an example, that's the magnesium-2 resonance doublet, the 3s3p resonance doublet at 2800 angstroms. And those synthetic spectra show that as you decrease that magnesium abundance by even 10 orders of magnitude relative to the sun, you could potentially still detect those lines or press those detection thresholds 10 decs lower than the solar abundance. So let me put this another way. If you find a candidate metal-free star in or near the Milky Way, the UV is the way to go to demonstrate that there really are no metals present in that star. I think the future for studying the origin of the elements is bright, especially in the UV. Thank you.
Thank you for this very nice talk. I'll open the floor for questions, particularly from students, postdocs.
Thank you for the talk. In the examples that you gave for the 5 UV elements that like you showed in the previous section, how do we calculate the areas for the UV detections? Because you specifically showed the relation between like metallicity and the chemical abundances of those 5 elements, and you showed some smaller areas for the UV detection, UV detectable areas. How do we exactly calculate them? Yeah, I'm basically talking about these blue areas. Like,
Yeah. So that is me showing you which of those points, individual stars, required UV to have a detection that made it on that figure in the first place, right? So in this example, from the ground-based near IR lines of phosphorus, you get everything that's not in the blue box. If you don't have the UV, you have no idea what happens at lower metallicity. That's what those, it's not a calculation so much as just trying to highlight the region of parameter space where the dots.
I was thinking like maybe some calculations is required for the UV regions, but yeah, okay. Thank you.
To guide the eye. Yeah.
Get money.
So the R and S and I process, like physically, what is the difference? Is it, and what is it mainly determined by? Is it just the neutron density, and in observations when you say, okay, this is clearly an R process going on? Like how do you see this? Is it just like a modeling assumption, or yeah, that's what.
Yeah, the difference between the R, S, and I processes. So theoretically, right, if you're a simulator or modeler dealing with a nucleosynthesis, yeah, you tend to think of those in terms of neutron density or some other related property that correlates with neutron density. So the S process, you have neutron densities, 10 to the 8, maybe, neutrons per cubic centimeter. The R process, 10 to the 22 to 10 to the 28, somewhere in that range. I process is, like the number that always gets thrown out as sort of the coincidence that comes out from the modeling is about 10 to the 15. Whether or not those are the only distinct regions of parameter space where the neutron capture processes operate, maybe not quite so distinct, but those seem to be the three that at least happen frequently enough that they produce something that we see, and that's the signature that we model. So that's the that's the theoretical picture of this. Observationally, it's you compare a prediction from one of those simulations or models and say, it looks like this curve, or it looks like that curve. Does this look like an R process or an S process? There's more to it, but that's the two-sentence version.
And the neutrons that from the neutron density, like where do they come from? Is it very distinct? Like what kind of astrophysical, or like star environments where you have R versus S process, or do they exist, both of them in the same place? And
the neutron densities are set by the physical conditions and the availability of free neutrons, right? You take a neutron out of the nucleus, it's radioactive. So you need some source of neutrons. For the R process, it tends to be the birth or death of the neutron star. For the S process, it tends to be neutrons liberated through some alpha N reaction on something in the outer layers of an AGB star. For the I process, you have protons being convectively mixed into the helium burning layer, and 3 reactions later, you have another alpha N reaction that kicks off neutrons. And so those different sites give you different neutron densities, different conditions, different time scales. That gives you different nucleosynthetic outcomes.
I find it very depressing that it's so difficult to get spectroscopic observations in the UV. I mean, you mentioned IOE long ago. You mentioned Hubble Space Telescope, which will not last forever. And then when you mentioned the new project, you mentioned probably it will have that spectrograph, but not even that is so. Why is the UV community, spectroscopic UV community, so unsuccessful compared to other ranges of the electromagnetic spectrum?
I suspect it has to do with the way science is funded and the scale of the budget that you need to go above the atmosphere. When you can do a ground-based facility of order tens to hundreds of millions, right? That's a huge sum of money, but it's attainable. There are missions, so there have been and there are other UV missions in operation, right? They tend to be small, even to the size of CubeSats. And only photometry, because you have a limited size, limited mass budget to actually launch. When your launch is half or more of your budget, right? You want to launch something small if you can, if that's good enough for your science. And for UV spectroscopy, particularly high resolution UV spectroscopy, you need lots of photons, large aperture, and now you're talking billions of dollars or euros.
Ian, thanks for this very nice overview of UV spectroscopy and what it can do to us to learn about stars. I have two questions. Let me start with, of course, a first star question. And I very much like the prospect of, going to the UV to find with the Habitable World Observatory many more of potential candidates. But what about the candidates we have, right? I mean, these are all low mass stars because otherwise they must be long dead. So these are all stars that are below 0.8, 0.7 solar masses. They will be very faint, and there have been many of these candidates studied up to a degree that we can probably already say with some confidence that the first stars have not been in this mass range. So I'm wondering what the Habitable World Observatory would bring new to this game. Do you think it's too early to close this chapter of very low mass population 3 stars? How would, what has been missing in the optical surveys to really detect the first stars? Because we do have lots of statistics, right?
Correct. So I guess it's important to draw the distinction between, do low mass population 3 metal-free stars exist, and what is the nature of a pop 3 star? So do those low mass stars exist is sort of a binary question, and you have a yes or a no, and if you have not yet found a candidate, then you're just playing statistical games to try to place, confidence limits on some IMF for some model of star formation. So I think that is a game we can continue to play from the ground. And I think the ELT and GMT, TMT, if they get built, will have a lot to say in that, because you can do relatively large surveys of very faint stars that would otherwise be difficult to do with sort of the 8-meter class telescopes. So I think that is one way forward from the ground that will continue to happen. The UV piece is more in characterizing. I think it has more of a role in characterizing the low mass stars that do exist, either first stars, metal-free stars, should they exist, or their second generation chemical descendants. So if we never actually find a first star, either because those metal-free stars that are low mass don't exist, or because we never actually can isolate an individual pop 3 star at Z of 15 in some lensed system with JWST, right? You need some alternative. You can think of this as sort of a risk assessment, right? You're giving yourself another way to characterize what those first stars are like, even if you never actually find one. And I think the UV gives you a lot more handles on characterizing.
Thank you for the interesting talk. My question is kind of related to some of the things we discussed here. It's kind of what would be the next big transformative step that would push UV spectroscopy? Is it simply having much more data? Is it having more accurate line lists? Is it better atomic models that would allow to do full 3D NLT to kind of push the accuracy of the abundance? Is it something else?
All of the above. I think most important of them, I mean, I'm not someone who is going to push the development of models, right? So I totally respect, I have, you all are my heroes, right? For developing these new models of NLTE and advancing the model atmospheres and everything. Without that, it would be difficult to interpret any of these data. So all of the above, I think the piece that the UV we can push on really is we need more data, right? Hubble has an oversubscription rate of 6-to-1 still, right? That has not changed with JWST. JWST is now 13-to-1, and so it makes 6-to-1 looks like oh great, I can do this. But the oversubscription rate has not gone down, and Hubble does have a finite lifetime. The current reentry probabilities that I've heard as of last month are sort of late 2033, and you stop doing science at least 6 months before that, there's a possibility of a boost. Who knows? There's what's going on in the US system right now is anyone's guess. So Hubble is going to be the only source until it goes. After that, you have these other missions, UVEX in particular, that can do some low resolution spectroscopy, but nothing high resolution. And Habitable Worlds doesn't come along until the 2040s. My goal is to survive in this field until, and maybe not retire before that happens. And that's no longer as much of a joke as it used to be. So I think just having more data on more stars, right? The ability, let me put this a different way. Having the ability to choose which stars you observe because they are scientifically interesting would put us in a very different place than we are now, which is we have to identify which stars we can observe and then try to identify science cases that will justify them being observed with Hubble. So if we can get to a regime where you can observe any star in the UV at the same quality UV spectrum that you can get from an optical spectrum from the ground today, that's a game changer because you now get to pick your targets.
Amazing work. I have an abundance question and a telescope question. In your abundance slopes that already go back to Camilla Hansen's work from 2012 on silver, when you group together certain elements, for example, gadolinium, dysprosium, you name it, aren't you already presuming that within that group the elements are co-produced? Do you know that kind of in group E, they are all the same?
So the figure that I'm not showing you here is one where we did this for each element individually. And within those groups, individually, they still show that same behavior. And so that guided our decision of which ones to put in group A or B or C or whatever. So the significance is lower, but it's still significant for nearly all of these when you do it individually.
No, definitely convincing. And then to the telescope, if you build a huge telescope that is supposed to be sensitive in the UV, isn't that a huge challenge to the coating of the mirror? Is that feasible these days?
It is, and the aerospace companies seem to have ways of doing this. That's not my field of expertise, but when I went to the Habitable World Observatory 2025 meeting last year, it was the science people, the engineering people, like it was the NASA people, and no one seemed concerned by the coatings. I mean, it may not be radiation hardened fully yet, but no one seemed concerned that they won't be at a technology readiness level by the time you need to freeze the design in a few years.
Right. I think we'll have one last question from Fritz.
Yes, thanks for your talk. I'm interested in the super heavy elements. So you actually explained how you find the fission products of those. How well is it possible to constrain how far it went up the nuclear chart and whether this fission recycling really happened there? And so how constraining can the observations be for that?
Yeah. So all we've been able to do so far is just add up numbers, right? 110 plus 150 gives you 260. Those are the sort of the minimum number that you needed to do that. To do that properly, the exercise you were describing properly, you need, proper R-process nucleosynthesis models that populate different ranges of heavy transuranic masses, and then do the fissioning of that. And those are separate questions from the nuclear physics point of view. They rely on us, the astronomers, for the constraints. We rely on them to have the nuclear physics, and it's this dance back and forth. And it's everything that you model at that point from the nuclear physics, I think, is an extrapolation. Whatever was learned from all of those bomb tests last century has mostly not been declassified. There's a little bit that made it out. Well, that was intended to be made out. But I don't think there's a whole lot that's been released from that. And at any rate, they have not said that they detected anything heavier than 257. So to do this properly, you really need the nuclear physics. But that is the route, is through more careful modeling. And then you have these signatures that you can produce, and like, what is the heaviest you are required to go to produce the signatures? What is the heaviest you can go to reproduce the signatures? And maybe that gives you some range.
All right. So I see on the board here, there'll be dinner with the speaker. If you're interested to join, then talk to Norbert. It'll be at 6:30 at this vegetarian restaurant, Red. And so with that, let's thank our speaker again.